Simonovitz conjecture and the Bourgain splicing problem. Boaz will give the talk remotely. Boaz, floor is yours.
Thank you. Thanks. Can you hear me?
Yep.
Yeah, very good. Okay, yeah. So indeed, I'm going to talk about the Bourgain splicing problem and the KLS conjecture, which is solved out of Polylog, and this is joint work with Joseph Lehek. And actually, I want first to thank the organizers for inviting me to speak about this topic. This is not a completely obvious choice of a topic for a workshop on quantum and crypto and lattices. And my hope is that you guys would ask me questions and make comments and stop me whenever you want. And also, there is a chat and Q&A, so people can interact using this way too. So I understand there is a microphone going around and that is being passed around. So if anyone has anything to say, then please ask for the mic and ask it. Okay. So let me start. So what's Bourgain splicing problem? So that's the following question. Is it true? So this from the 80s. He came to it through his work on maximal function inequality. And he asked, is it true that for any convex set, K, it is convex and has volume 1 in Rn, and n is a large number. Dimension should be sort of a large number, as is common in complexity. In fixed dimension is a trivial question. That any for any convex, you can find a hyperplane section whose volume, the volume of the intersection of K and H, is at least C for universal constant C. So can you find, you have your convex set, and you want to find any hyperplane H where the volume should be at least a universal constant. Okay, so this is Bourgain splicing problem, and it may look like a riddle if it's the first time you see it, but it actually does have a few consequences, implications, and relations to other problems in convex geometry in high dimensions. And let me just tell you about some equivalent formulations to demonstrate its role in the theory. So the first equivalent formulation is the corrected Boson-Petty problem. So Boson-Petty problem was a problem from the 50s so suppose that you have suppose that K and T are two convex sets in Rn. Let's make them centrally symmetric, although centered is fine. Bicentered origin is fine, and assume that for any hyperplanes through the origin, if you take the volume intersection of K with this hyperplane, it is smaller than the volume of T with this hyperplane. If I put these two bars, I mean the size of the object. So it's n-1 dimensional volume here. It must be right. It's a hyperplane. So you know that for all sections, the volume of K is smaller than the volume of T. So is it true that the volume of K is smaller by some universal constant times the volume of T? It was first conjectured with constant 1, and this is indeed true in some cases. If K is a Euclidean ball or cross polytope, then it's true with constant 1. But after lots of work, it has been discovered that this is true in dimensions 1, 2, 3, and 4, but from 5 and above, it's just false. In fact, dimension, I don't know, 20 and above, the counterexample is simply the cube and the Euclidean ball. So K should be the cube here, not Euclidean ball. Okay. So this is, and if it's up to universal constant, then this is equivalent to the splicing problem. Second equivalent formulation is let's say, refined Millman ellipsoid or M ellipsoid. So this is the following question. So again, K in Rn is convex, volume 1. And the question is, does there exist an ellipsoid of volume 1 such that volume 1, so that if you intersect it with K, it captures, so the volume is 1. And what you want is that if you intersect K with some enlargement of the ellipsoid by a constant factor, this is the volume at least 1/2. Okay, so this is equivalent to the splicing problem. And if you would put here power 1 over n, then this is true. This is the Millman ellipsoid. But without this power, this is not normal. Usually you can capture half of the mass of a convex set in an ellipsoid of roughly the same volume. The third equivalent formulation is the Silvester problem, which is the following question. So let's select n+2 IID independent distributed points, random points in some convex set. K in Rn convex. And you ask for the probabilities that are in convex position. So this is the probability for convex position. What does it mean? It means that, say in the plane, it is 4 points, and they are in convex position if no point is in the convex hull of the other points. This is convex position. And the slicing problem is equivalent to the question whether this, actually the complement, whether 1 minus P of K to power 1 over n is theta of 1 over root of n. So it is bounded from below by some universal constant times 1 over root of n. So that's another formulation. And I think the last one would be about the entropy and covariance. So this is about low concave random vectors. So suppose that X is a random vector in Rn with a low concave density. Okay, so what is a low concave density? This means that it's E2 minus H, where H is a convex function. So it looks like the Gaussian, say, or something. This is a Gaussian is low concave, and also the uniform measure on a convex set is again low concave. And this class of low concave densities, low concave random vectors, is stable under various operations. So if you take the sum of two independent low concave random vectors, it's again low concave. If you project it to a lower dimensional space, it stays low concave. So there's a convenient class of distributions, which includes uniform measures of convex sets. And the question, so is it true that you can determine, so do you know what's entropy of a random vector is? If X is density F, then the entropy is just the integral of, what Weizmann, Shannon, F log F on Rn. And the question, is it true that for any low concave X in Rn, you can determine its entropy with some small error by the covariance matrix? So is it true that the entropy of a vector is half of the log of the level of the covariance matrix of X plus a small error of n? Okay, and covariance, should I define? So there's no interaction at all in the first 3 minutes of the lecture, which is a bad sign. So please say something here and there. So so this is a matrix, and the IJ entry is just this is the covariance of this time actually. And INJ Rn from 1 to n. That's the covariance of the vector. Okay, so both entropy is a way to measure the size of a distribution in Rn. So kind of if it's uniform in some set, then the entropy of the distribution is just the log of this volume of the set. But also the term of the covariance matrix is a way to measure the support of a random vector. And slicing is about the question whether you can replace the two more or less up to a small error. Okay, so these are 4 connected formulations. So all of them are now have positive answer up to logarithmic factors, the last one up to log. But let me, just to connect to lattices, let me add a remark. And in fact, there are greater experts than me in this audience, particularly Stefan Davidovich. So it is not, so they proved, Greg and Stefan Davidovich proved based on works of others, the following conditional statements, that if among all uniform measures on convex sets, on symmetric convex sets, you know that the entropy, this difference is maximized for the cube. So this is a strong form of the slicing problem for the cube. Then a certain old conjecture attributed to Minkowski follows. So Minkowski lattice conjectures follows. I guess that, okay, I can tell you about this conjecture if you want to know. So the conjecture says that for any lattice L of determinant in Rn determinant 1, of call volume 1, there is a and for any translate, then the translate of L intersect a certain set, and that set is all points in Rn whose geometric average is at most a 1/2. Okay, so that's one relation to the.
Boaz?
Yes.
So, hi, by the way.
Is it Greg? Greg?
Yeah, I'm Greg. Yeah, okay.
Thank you. Yeah.
Is this case 4? Is this like a restatement, at least for uniform measures and convex sets? Is this convex bodies? Is this the same thing as the isotropic constant conjecture? Is
Yes.
Okay? So that really is fully equivalent to up to a constant factor to this Bourgain slicing and all of the other.
Exactly. This is a topic constant question. Right. Yeah, but this is so here the scale it's more the log of the topic constant. So you want to, so this is known up to log n basically because it's already in the logarithmic scale because you took logarithms. The isotopic constant, so if just because Greg mentioned it, so the isotopic constant of K is the determinant of the covariance matrix of the uniform distribution on K power 1 over 2n over its volume to the 1 over n. That's the isotopic constant of K. And indeed, when you're uniform, the entropy is just the volume. So you see that these are the same things.
So isotropic constant is yet another thing that's in your laundry list of equivalent to the slicing conjecture.
Yeah. So the number 5, thanks to Greg. Yeah. So is it true that that for n, and it is always at least, this is true, it's at least universal constant. Is it true that it is also for any K in Rn, this is at most universal constant? That's the 5th equivalence formulation. Good. Okay. So now either we work. Okay, so let's either work with LK or let me put it. Okay, so let's define. I would not work with a topic constant. I work in slightly different. It's equivalent to universal constant. So I go over all convex sets, and for each of volume 1, for each I try to see what's the section of largest volume. And that's this one. This 1 over that, and this is this quantity. And our theorem is that this is bounded by constant log to the 4 times n. Okay, so up to log factor, you know that for a convex set you can find a section of whose volume is at least 1 over log to the 4. Previous results, so Chen, just less than 2 years ago, had a very good bound. It was a breakthrough. So he got that this is at most root of e to the root log n. So it's smaller than any power of up to log n. So this is smaller up to this is smaller than any power of n, which was great progress because the earlier bounds was by Bourgain and myself. So Bourgain in the 80s proved that this is at most n to the quarter log n, and I removed the log n at some point. Okay, so so this is about the isotopic constant. Now, so there is a hierarchy of open problems in spherical geometry, and the slicing is not very high in the hierarchy, so there are harder problems. And in fact, theorem 1 follows from the relations to things from thin shell and KLS. So let me explain what these two things are. Which are how Yes, please. Yes.
Quick question.
Not quick, please make it.
Does the probabilistic method give you anything sort of, is there a sort of a simple bound that you can get by sort of picking the hyperplane sort of at random, however you?
Yeah. Okay. So there is one complete trivial bound is root. So first of all, in a fixed dimension, it's a trivial. You can find a trivial bound is that this C here is one over root of n. Let's see why.
Right.
One over root n is trivial. Why? Not I mean easy. Like the first thing that you one over n is because the Euclidean ball of volume 1 has radius root of n. All right. That is people know these things. Right. So the Euclidean ball of volume 1 is radius root of n. So this would mean that basically, if your convex body is volume 1, then there is a direction in which the width is when you take two hyperplanes, what's the distance between them? So there is at least one direction where the width is at most root of n, because otherwise we have too large volume. So if you have a direction where the width is root of n, by Fubini, one of the sections will be at least 1 over root of n.
Right.
Okay, so that's the first bound ever. It was not even mentioned anywhere in the literature. Bourgain got the n to the quarter, which was kind of a non-trivial thing. And at some point, there was 3 completely different proofs that led to this n to the quarter. So Bourgain's proof used a certain moment by telegram, measuring measures, geometric chaining, things like that, bound by PZA. And then my approach used the logarithmic Laplace transform. And then there was another proof by Lee and Vempala, which was that's considered idea. And all of them gave n to the quarter. And there was some kind of people thought that, well, maybe that's n to the quarter is the right thing. And the natural counterexample was something like some convex set of matrices in dimension n square. In dimension n square, root of n is some natural scale you see in random matrix theory. So somehow this was attempted, but no, Chen just found and actually used things which are not that far from what the experts tried, and he just broke this barrier and got something which is way less than the end of the quarter. And today we improve it a bit further and get log into the fourth. Anyone else? Some question? Okay, so I tell you that there is this Ln, which is about volumes of sections, and the hierarchy. So there are things which are weaker that are all dissolved, we'll discuss them, but the things which are still open are there is something called sigma n, which is thin shell, and there is Cn, which is KLS, constant, Kanan over Simonovich. Okay, this implication is due to Ronen Eldan and myself some years ago, and this is kind of simple. This is very relatively easy. Okay, so what are these things, thin shell and KLS? So definition. So let me say that a random vector X or probability measure. Would you prefer random vector probability measure? Not clear. So probability measure mu is isotropic. Is isotropic if it is centered and covariance is identity. So this means that the integral of xi d mu x is 0, and the integral of xi xj is the delta, is the Kroneker's delta. Okay, so this is just means that you translated your distribution to make it centered, and then you rescale linearly in some orthogonal directions and made variances equal 1 in all directions. Okay, so this is isotropic. And now the thin shell constant, so if mu is low concave and isotropic, so normalized, if thin shell constant, sigma of mu, is just the variance of the Euclidean norm. Okay, and actually it's also equivalent to universal constant by reversal inequality for polynomials to the variance of the square, the norm of square divided by n. So what is the meaning of this quantity here? So let's try to draw a picture. So maybe this is the axis, and mu is some measure here. And since it is isotropic, you know that the expectation of x squared is n, is exactly n. So basically, the Euclidean norm of x is typically around root of n. That's the scale in which this distribution lives. And what the thin shell conjecture suggests is that there are two concentric Euclidean balls. So both of them are roughly root of n, and the width, the distance here is sigma of mu, and half of the mass, most of the mass of this distribution lies in this thin spherical shell between two concentric spheres of comparability, and the difference is sigma of it. So that's why it's called the thin shell constant. And some years ago, it was shown that, okay, I'll discuss this in a second. So that's the thin shell constant of any distribution mu. And sigma n is just the supremum of sigma mu or all mu in Rn. This is this thin shell parameter sigma mu. And the effect that was discovered like 15 years ago was that indeed the shell is thin. So comparable to the radius, which is root of n, most of the mass for log concave case is indeed containing a thin spherical shell. And the game is to show it's really thin, to control the exact way the growth of this parameter sigma n. Okay, but the fact that sigma n is little over root n is kind of important. Okay, now what's the KLS constant? So let me start with the isoperimetric or Chigger constant in some communities. So that's the following quantity. So our measure would have, or random vector would have density rho, that's the density. And we define the isoperimetric coefficient to be just, you take all sets in Rn of smooth boundary, all subsets, smooth boundary, and you look at the following ratio. So you look at the boundary measure, so the integral over the boundary of rho, divide by the minimum of mu of A and 1 minus mu of A. Okay, so if I draw a picture, so I have my convex set, and I look on all possible ways to partition it in two parts so that the interface will be minimized. And in fact, it is known, actually, in the convex, it is known that influence is that, okay, known, Sternberg and Zumburg, it is known due to the result of Sternberg and Zumburg from the end of the 90s, and in the convex body case and in the low concave case, it was generalized by Immanuel Millman, that it is, it is essentially enough to consider mu equals 1/2. So it is, with some extra little quality, it is attained where the partition is symmetric, half and half, this ratio here. So that's the isoperimetric constant of distribution. I'm sure that people know that. And psi n will be, well, the supremum over psi mu over all low concave isotropy distributions. Okay, so that's mu is low concave isotropy. So these are the three open problems in volumetric convex geometry in high dimensions. So this is hyperplane sections, this is thin shell, and that's isoperimetry of all possible sets. And this is known that we have these relations. Eldan in 2013 in his PhD proved the following important inequalities that you kind of can reverse this thing can be reversed up to log. This was known already almost 9 years ago. That psi of n is at most up, so this means that up to constant factor, sigma n times log n. And for that, he invented a method called stochastic localization that we might discuss later. I think, yes, believe it. And our theorem is that, theorem 2, is that up to polylog factors, these things are bounded. So Pn is log to the 5 we get. It's not, I'm sure the powers are non-optimal. And for sigma, you get log to the 4. Okay, so actually use Eldan to get from this bound to the psi bound. Okay, so let me tell you a bit about bounds for sigma. Any questions about? Okay, so,
yeah, Boaz.
Please, Brad.
Two questions. One more strictly mathematical, and one maybe a little bit just about your opinion. So there's a way to convert or approximately convert a log concave measure to a convex body.
That's right. Yeah.
You just take extra dimensions and then you just make it
Yeah, there are many ways.
a surface of revolution so that you rescale
Exactly.
balls according to the probability destiny.
Yeah.
Is this conversion a universal principle across all of your talks so that you can always say
Yeah.
that log
Any
concave measures are the same topic as convex bodies for everything you're doing?
Yeah, pretty much.
So
yes.
maybe simply the log concave measure is a more convenient viewpoint, but not fundamentally different, I guess is what you're saying.
Yeah, although you can, I mean, if you really insist, you could find it, but I mean, yeah, I agree with you. Yeah, it's the same thing. Log concave measures and convex information, for me, it's more or less the same thing. And
Okay, so maybe I have actually two opinion questions rather than just one.
okay.
So to follow up on your first answer, is do you consider log concave measures a better viewpoint after a while than convex bodies, or
Analytically, it's much more convenient. You'll see from the proof. Yeah.
analytically
In my proof, yeah, you definitely need to you have the Gaussian, you want the heat flow. I mean, you don't if you, I mean, many techniques just immediately leave the realm of convex bodies.
Okay. So even though it's sort of universally
all these
equivalent,
conjectures,
you do like the log concave measure viewpoint better, I guess.
yeah.
Okay. So my other opinion question is that
Maybe just one little remark. So all of these conjectures are equivalent up to universal constant for convex and for log concave. So you can prove slicing on essential for one of them.
Sure. So my other question is, before any of this revolution, you told me that some people were starting to wonder a little bit about the slicing conjecture because it seemed too strong, was your phrase, and maybe it's not true. So is it your opinion now that for, you know, that probably you can get rid of all of these log factors, or does that still seem too strong? I mean, do we understand these conjectures better by believing them without any of the log factors? Or does the revolution with the log factors, is that taken as evidence that you should even be able to get rid of the log factors, and that the conjectures are really true without them?
First of all, the powers, I'm willing to bet they're wrong. So
It's
the
sort of
5 and the 4, I'm sure that they're not optimal. Now there are 3 conjectures there. By the way, if I would put something here, it would be the Bourgain-Millman inequality. Basically, that's the thing which is kind of weaker than slicing, in my viewpoint. It's hard to tell, you know, they say that if the problem is hard enough, it's not so important what the experts think. I'm afraid to, so some people, you know, okay, so I don't know, KLS, what conjecture this is true in 95. This looks strong, and this looks, I would not be surprised if slicing is true. For KLS, I don't see any, for KLS, it looks to me hard, at least to prove. For slicing, it could be, even for sigma, and for these two things, it could be not something spectacular. Even there could be some simple argument that all of us missed. It's basically optimization of some not that complicated parameter in the space of convex sets. After all,
well, let me just put it this way. This is a kind of more radical assertion about what people should believe. For some of the most famous questions, whether it's the Riemann hypothesis or P versus NP, there's a feeling that you understand the question better if you believe the conjecture.
Ooh. How about factoring is hard?
Well, it's not true for all conjectures. I mean, particularly if eventually there was a counterexample. Then in hindsight, then you cannot say that you understood it better if you believe the conjecture because it's the wrong answer. But certainly, the feeling is that you understand the Riemann hypothesis better if you believe it.
Yeah.
You're not going to go this far with any of these conjectures.
I didn't check 10 to the 10 roots or anything. So,
okay, you're hedging, so you're not going that far, even though you have this log
going
factor.
that far. So, but you know, I mean, somehow I put a gap between these two things and that thing. So for me, Allen and Sigman are more kind of less. I mean, I think that let's say I would spend my time on proving that these are bounded, let's say, more than on finding one of them, but for sigma cyanide, I'm not just don't know. That would be
Okay, thank you. That answers the question.
but I wouldn't say that I put more than 80. I mean, it's not that I would really, I don't know. Yeah. One good thing about this problem is that there is kind of a steady progress, more or less. So it seems, so if you look at, on sigma n, then the sigma is basically the width of the shell, and root and bound is a trivial thing. And let me just tell you that, I mean, yeah, so in 2007, the first non-trivial bound was n to the 2/5 plus little of 1. In 2009, Bruno Fleury from Paris improved the exponent to 3/8. This is really an improvement. It's an exercise for you. Okay. Then n to the 3rd was Godin and Millman in 2 years later. And these techniques used, and by the way, I was certainly personally influenced by Paru's large deviation estimate. So which happened earlier. It was in 2005. So this was, he got not essential, but some kind of large deviation, which was really, really influential for me. But these three things use basically the same technique, which is some kind of concentration of measure in high dimensions, things like that. And then there was some break of 5 years where Eldam did this method, and then it was used by Lin and Vempala to get a clean end to the quarter. So we thought it's clean at the time. And then in Chen in 20 got that. So this was the break, so he got it for all of them, even Psion. Okay, so like this sigma is more than Psion. It's more than e to the log n to 1/2 plus of 1. So this was really a break. Okay, so if you look at this, you have some statistics, so you could conjecture that, I don't know, in like some 3-4 years, and it will be first improvement, and I do believe that it's not a fire. Good. Okay, so for now, let me discuss a bit about the proof. Other questions about the formulation of the results and history. So by the way, I mean, it's problems that interest seems to, these people, some of them belong to the part of math, some in computer science, some in statistics. So it's a problem that has people from different angles were able to make progress here. So yeah, it's not that far from you guys, I'm sure. Okay, so the approach that we have, our approach relies on some functional analysis and probability. So we use something which I call H-1 inequality and Eldam's theorem. Okay, these are two things that we rely on. So let me begin by recalling the Poincare constant. So the Poincare constant, I'm sure you know it's on a graph. So what's the Poincare constant CP mu? So for any probability measure, this is the minimal number C for which the Poincare inequality holds. So I want that for any function f, its variance should be smaller than this constant C times the integral of its gradient square. Okay, so on a graph, you sum of all of the edges, look at the difference, right? And in the continuum, look at this integral of gradient square. This is a Sobolev norm, if you, it is denoted sometimes by H.1 of mu. Okay, so that's the Poincare constant. And the Chigger inequality may be reversed in the low concave case by results of Boozer and Ledoux from the previous century. And they say that basically the Poincare constant up to universal factors, I think 4 or 9 or something of this sort, is basically this isoperimetric constant that we mentioned earlier. Okay, so if you know that your convex set has good conductance, that the interface of two sets of measure 1/2 is always large, then you know that the Poincare constant is large, and the other way around. Up to constant factors, these things are the same. And the KLS conjecture, so I didn't say that, it says that, okay, psi n is bound by universal constant, but it also means that linear functions nearly saturate the Poincare inequality. So why? Because if your function is x1, this is a linear function, just x1, right? So if you took x1, not in red, still, yeah, then its gradient is just, this is just one, the gradient is just one, and its p-isotropic, its variance is also one, so these two things are one. And the conjecture is that, well, this is roughly the extremal case. Okay, so that's the kind of Loewe-Simonovich conjecture. Okay, good. Now I want to dualize this H1 norm, if you would allow me. So my point of view is a bit kind of function analytic, but there is also a lot of probability. So I think this point of view kind of complement each other here. So the dual norm is the H minus 1 norm. So for if you have some function f, we can make its integral 0, so it's not that, otherwise it's infinity. Then the H minus 1 norm, what is it? So it's the dual norm to the H1 norm. So I look at the supreme over all functions of the integral of u times f. Over all functions whose H1 norm is at most 1. Okay, so this is a dual norm. Okay, why is it? What's the meaning of this norm? I'll say so. This is infinitesimal transport cost. Actually, this is the meaning of this norm. So if you look if you have your measure mu, and you want to find, and you look at another measure 1 plus epsilon f times. So this is again probability because of this condition, and you want to say what's the best way to couple them so as to minimize the squared L2 distance. Then this is called the Wasserstein metric. Then this is indeed roughly epsilon times the norm. Okay, so that's the meaning of this inverse Sobolev norm. Okay, now there is an inequality called the H minus 1 inequality. So it was proven by myself in 2009 for convex sets and by Bart and myself in the local case. And indeed, as Greg knows, this is the same proof, not that complicated. And the thing is that if mu is low concave,
Boss, just a second. So can you remind us of what the definition of H1 norm is?
Integral. Okay, I will just not write it. Okay, let me write it within your. Okay, but integral of gradient square is good enough for you, right? Sorry, that's H minus 1 norm. Just the integral of grad. Maybe I'll put it in bigger letters. Integral of grad u square smaller than 1. Okay, that's so you. All right, so the H1, the Sobolev 1 norm is okay. What the 1 means, first derivative. That's what it means. So functions in H1 mean the first derivative, the L2 norm, of the first derivative. That's the 1 here, and that's the minus 1 is kind of the L2 norm of the minus 1 derivative. If you but this is it. Okay, so you just look at the dual norm, take the supreme of the scalar product in L2 over all functions whose gradient is L norm at most 1. That's the H minus 1 norm. Never seen that, huh? Okay. And transport, I think, right? Transport is something that people. It's a very geometric thing, right? You not want to couple two measures and to minimize the distance. That's something that people see quite often. So that's the meaning of this norm. Okay, and for low concave measures, these norms behave. There is a nice thing, which is that for any function f, its variance is at most the H1 norm of the gradient of the function. And this means that this is the sum. This means this is the sum of the coordinates, H minus 1 norm of the gradients of the coordinates. And maybe let's assume, okay, say assuming that the integral is 0, otherwise it's infinity. So it's not assuming the integral of grad f is 0. Otherwise it's meaningless. Okay, so we claim something a bit strange. So let's look at units. Grad f is 1/meters because we divide by something, but the H minus 1 norm exactly brings the back. So this is the same units as the left hand side. So it could have, this is not the others. This is just for low concave. And should I let me just to show kind of what techniques are being used. Just tell you the proof is really simple. I mean, it's so general. It must be simple. No constant. So there is, when you work with graphs, you have that, that the Poincare constant is 1 over the first eigenvalue of the adjacency matrix. right? Of the looks like a spectral thing. So what's the adjacency matrix of a measure? Well, the adjacency matrix is an operator, which is this operator. It's Laplacian of mu plus grad u times grad log of rho. Okay, this is the Laplace type operator associated with the measure mu. It's sometimes called Fokker-Planck or Langevin. There are some names that you can attach to it. And the interesting thing is that there is some in the low concave case, there is a Bokeh formula, which says that for any u, the integral of LU square. So it exists in the discrete world. I even wrote a paper about the discrete world, but it's kind of in the continuous case, it's much more developed. So this is just an identity. It's you take the second derivative of the function and you add the mu, everything the mu. And if rho is e2 minus psi, then this is the Hessian of psi grad u. And this is positive in the low concave case. So you have this inequality and you just dualize it in using such definition, and you get, I mean, it's really few lines if you are familiar with these techniques, kind of classical functional analytic techniques. Okay, so we have some kind of relation between the variance and the transport cost of the grad of the function. Right, something else. And now what we're going to do, we're going to combine Eldon's theorem with H minus 1. So far, Eldon is a black box because I didn't tell you about localization, but H minus 1 equality, I hope you kind of agree that it's not that difficult. So how would I combine these two things together? So I have a measure mu, low concave isotropic, right? And I want to prove it's in shell constant, bound, things like that, KLS, whatever. Let me take a measure which is pretty much the worst possible, the one with the largest thin shell constant. Okay, so the thin shell of sigma mu up to some factor 5 or 2 or 1 plus epsilon, okay, is as large as possible, the thin shell bound. Okay. Now, so what do we know by Eldon, which is still a black box? So we know that psi n up to log is and sigma n are roughly the same. Sigma n squared is at least psi n squared over log n. And this is sigma mu of square, okay, which, as you remember, that's the variance of x squared. Okay. Thinking with my definition, it should be up to universal constant because the different difference. Okay, but this is clear. So that's the definition of sigma u, the variance of the square norm, the of the thin shell. But now let's use this h minus 1 inequality with the function x squared. The function x squared is a very simple gradient. It's 2x, right? So this is at most 1 over n times the 4 over n, I'm sorry, times the h minus 1 norm of this random vector x, right? That's something helpful. So this implies that if I look at okay, the h minus 1 of x is, let's look at the average of the h1 minus 1 norm of the coordinate functions, which have a mean 0 because the measure is centered. A trivial fact that this is exactly bounded by the Poincare constant, because if you remember this, I mean, I'm sure it's difficult unless you are really geniuses to immediately understand that when you dualize and you look at the Poincare inequality, you get that the h minus 1 norm is at most the Poincare constant times the L2 norm, but believe me, it's just one line. Okay, it's very simple things that the h minus 1 norm is at most the Poincare constant times the L2 norm. That's a triviality. It's always true, but what we get from this chain of things, we get a lower bound, right, for these things. And what we get that this is at most, so at least even psi n, let me put the Poincare constant, which is slightly, could be a bit smaller than psi n over log square n. Okay, so this means that even if we didn't start the proof, just plugged in Eldon, and we already know that up to log factors, linear functions nearly saturate the h minus 1 inequality. Nearly saturate the h minus 1 inequality. And if you remember, the KLS conjecture is saying that linear function will saturate the Poincare inequality. So we kind of when you just use Eldon and as Eldon and H-1, you kind of immediately see that, well, up to log, things look pretty good, right? Up to log, you know, the functions satisfy the H-1 equality. So you need to find some way to kind of dualize it, this fact. So this will be our approach. Okay, so let's look at the spectral decomposition of xi. I don't know any one of them. I don't know, like a typical xi of one of these functions with respect to the operator L. What does it mean, spectral decomposition? So I put, I'll call it nu of xi. It's a measure on R. It is called the spectral measure of xi. And basically, ignore these things. It basically go over the eigenfunctions of the operator L. So these are the eigenfunctions, and I put this is the eigenvalues of L, of minus L. These are the eigenfunctions. And you know, I take the decomposition with respect to this normal basis. I look at the mass of the L, I look at the L to the composition of X in this basis, and these are the size of the coefficients, right? So for instance, I know that nu xi of R equals 1 because it's an L2 function of norm 1. Okay, so this is a measure. It's a measure, and let me draw this measure. So okay, let me draw the density of this measure, just a discrete measure, but let me draw, suppose you kind of convolve the tiny Gaussian or something, because I want to draw this picture. So that's this measure, it's density kind of. So how does it look? So I have 3 scales that I care about. There is lambda 1, the first eigenvalue, which is one of the Poincare constants. There is, say, times log square. And there is 1. 1 is a big scale, you know, in this graph. And this is some mass. This is nu of xi. The total integral is 1 here. Okay. And what do I know? So first of all, the mass of what happened? Very good. I know that the mass the mass starts at lambda 1 because there's no spectrum here. This is the spectral gap. And I know that the median, so here there is at least half of the mass. Why? So at least half of the mass is below log n times lambda 1. Why? Because we know that the harmonic, not just the median, even the harmonic average. So the H minus 1 norm, what's the meaning of the H minus 1 norm of xi? It is just the integral of this measure of 1 over lambda. Okay? And I know, okay, if I put, maybe I put it, let me put minus 2, so to be the harmonic average. Okay, and we know that the harmonic average is at most lambda 1 times log square n by the thing that we wrote upstairs. So we know that the harmonic average is good. This is not that big. And on the other hand, if I just take the expectation of this measure, then the meaning of this expectation is you go over the eigenvalues of, what do? You take the operator L, you go over all eigenvalues, you just put mass, which is the eigenvalue at each one. Then what you would get is just the H1 norm of mu, which is 1. So I have kind of median versus expectation. So I know that the expectation of this measure is 1. But the median is pretty small. I mean, it's lambda 1 over log square. And so I want to show that this cannot happen, that lambda 1 is kind of big if these things happen. Okay, so that lambda 1 is actually also up to polylog, is close to 1. So that's our situation. So what would you would like to kind of dump the high frequencies, right? I want to apply kind of heat. So that's what I tell you. I want to this is the only way I know. I want to apply some heat flow and say that these destroy high frequencies because they annoy me. I want to show that they do not matter that much. Okay, so let me tell you things about the heat flow in Rn. Okay, so this is a very common technique in analysis, also in combinatorics a bit, no? A bit. So what do? We have the Gaussian measure. This is Gaussian measure in Rn. I can still write the density if I'm, so it's, well, okay, of gamma S of mean 0, I will not waste your time, of mean 0 and variance S. Okay, so that's a measure of root of S width kind of, okay, in Rn. And now what's the heat flow? The heat flow is just converted with the Gaussian. So given mu is given. Now I look at mu of S, which is mu convolved with gamma S by biconvex bodies. It's not concave now. And I look at, I also want to look at the PS operator, which is, okay, this it looks like, what do I do? Why do I need to define PS and mu? That's because PS is a contraction from L2 of mu S to L2 of mu. This is, so I mean, this means that, well, so the integral of PS of F squared d mu is smaller than the integral of F squared d mu S, and this is for any mu, any F, no local concavity. It's completely simple, a very simple thing. Okay, and in functional analysis, people just dualize whatever they see. So let's dualize PS. Let's look at the adjoint operator. So we define QS to be the so-called adjoint operator from L2 of mu S to L2 of mu. No, sorry, no, this is the good thing. From this S goes further. Yeah, this is the from L2 to L2 of mu of S. And it's not that mysterious. I mean, it's actually a very simple thing. QS of F is just PS of F rho divided by PS of rho. It's a very simple formula. Well, rho, let me remind you, the density of your measure mu. Okay, so that's some operator. Let me define, and its meaning is through actually time inverted stochastic equalization. So now let me use this opportunity to tell you about these things. So actually this point of view is from papers that I had with Putterman a bit after Chen's result. So for any F, QS of F, these operators that we defined, the adjoint, this thing. So this is basically the, if S is 1 over T, this is the expectation of the integral of F times something called PT of X. Okay, or PT, where T is a dance stochastic equalization. Okay, what do I mean by dance stochastic? What is Lattice equalization? So it's something. It's a stochastic process. Okay, so let me use the last few minutes to tell you about this Lattice equalization. So PT is a stochastic process of probability distribution in Rn. And actually just a point of view for analyzing the heat equation of probability measures in Rn. The densities maybe in Rn. So how does it work? So let me write, okay, I'll write a stochastic differential equation because many people know this even in discrete world. So so I have some Brownian motion PT, and I begin at time 0, I begin with my P0 is just rho. And then at any little time interval, I'm going to multiply by my function, and AT is the barycenter of PT. And what is the meaning of this equation? It means that I begin with the probability distribution on Rn, okay? And then I flip a coin, and according to my coin, I multiply the distribution by an affine function in kind of a random direction, and still I'm guaranteed that the total integral will remain 1. So if you want, then PT plus epsilon of X is roughly PT of X times 1 plus, well, root epsilon, no, okay, X minus the barycenter times theta. Well, these are kind of this plus or minus, let's put it. These are random direction or something of this sort. Okay, so I multiply it each, ignore the root of epsilon for now. I just multiply the distribution each time by some random linear functional. And this is very helpful for analyzing the heat flow. For instance, because of the formula I showed you above, right? You get it from the heat flow. Some kind of reverses the time of the heat flow and let you use the isotropisticity of the measure in a very clean way. okay, so how would they dump frequencies and things like that using gradient heat flow? So there is the following proposition, which I from my paper with Puderman, which says that that if you have if you use low concave, and it takes any function, L2 norm is 1, integral of f dmu is 0, then for any number s, if I look at qs of f, sorry. So this thing, actually this is log convex in S. That's the two thing. There is some second derivative thing that reminds you of the Bokeh formula, and in particular, this is at least the exponential of minus S, the H1 norm of mu squared. From this we got a corollary. So using these spectral things that some kind of spectral truncation, kind of truncate them. You remember that graph I wrote earlier? There was a graph, and I want to get rid of some frequencies. So let me tell you what you get. I mean, just from this proposition immediately. So we got the following lyrical proposition 1. It says that same assumptions. Then for any S and lambda, if I look at the amount of mass, the spectral mass that F has in the interval 0 lambda, this is at most QS of F. No, this is up to a constant 4. So this is at most the L2 norm plus S times lambda. And what you do, well, another proposition that I'll not just say it briefly because I have just 1 minute. So this is thanks to Lee and Dan first, and Lee and Vempala, which kind of promoted very much this localization point of view, which was 16, and mostly due to Chen, who worked a lot on this thing. So they kind of bound, so for X, QS of X, they kind of, okay, I write the bound just because, but QS of X is really bounded by there is a good bound for that, whatever. I write it just because, so O star up to log. So there is some bound for that thing, and now you can kind of optimize in S. You get a bound for nu f of E lambda. So for any lambda, you optimize in S. You get the bound for this thing, and then comes the big pleasure. So to complete the proof, I just take really 1 more minute. Then you just argue as follows. You say that, okay, we had, if you remember, sigma n square was at most the H1 norm of that thing. F is X. Okay, this is the H minus 1 norm of X, right? But this just equals to the integral of the spectral measure of X. Okay, over from lambda 1 to infinity over lambda square. This is just some identity, and if you just plug in the bound that we get here, you get, well, whatever, you get sigma into smaller power, 8 over 5, which is smaller than 2, and then you're kind of done. So that's, I hope I showed you the kind of scheme of things that are used in the proof. So this is all I want to say, and thanks for your attention. I'm done.
What?
Yeah, wake up. Okay, yeah, thanks. Yes.
Any questions for Boaz? Okay, let's thank Boaz again. Thank you. Thanks for doing this.
Thank you guys.